All right, hello everybody. So we're gonna kind of briefly just kind of review 8.1, I think, and then before we go to 8.2. So all 8.1 is talking about complex numbers, and I'm assuming that if I have an equation, say like x squared is equal to -16, and you say solve of for all complex numbered solutions, that you take the square root of the -16 and you come up with 4i, right? Plus or minus 4i is the two solutions to that. Or if I were to, add, say like what's 2 plus 3i plus 5 plus 8i, all we would be doing is just adding those numbers. So 2 and 5 is 7, 3i and 8i is just the 11i, and that's it. What is multiplying the 2? Well, I could 2 minus 3i, 4 plus 5i, and I would just distribute that out. So it'd be like 8, 10i, minus 12i, and you got this minus 15i squared. But you remember your I squared is -1, so if you see the I squared, replace that with -1, so you got 8 minus 2i, and this is really minus 15 times -1. Really, that's just a positive 15 added on to the 8, which is just 23 minus 2i. So I assume you've seen something like that before, how to go through and do problems like that. So I don't want to spend a ton of time rehashing that. Maybe point out if you are asked to do maybe like one like this, 6 plus 2i over 1 minus i, how you would divide the complex numbers. You would start off by multiplying by the conjugate of the denominator, so 1 plus I, and then go through and distribute all that out. Okay, so that in this case I would have like a 6 plus 6i plus 2i plus 2i squared. 1i minus I cancels, minus I squared. So I end up with 2i squared is -2. So this is really 4 plus 8i divided by 2. And of course I could divide each one of those by 2, get 2 plus 4i. Okay. So again, not going to spend a ton of time on that because assume that you've seen that a lot in Algebra 2, and you will see it again in Pre-Cal. Actually, you guys already had Pre-Cal. Never mind. So you should know how to do that already. Okay, let's look at polar form, okay, of complex numbers. And I just want to kind of point out something real quick. So maybe I'll show you this picture. So I think it's pretty cool here. And that is to say, I might think about just adding two vectors together. So, what does that, or two complex numbers together, what does that actually mean? What is a complex number really? Well, I think before you've seen this picture where you said this is like the real axis maybe, and this is the imaginary axis, right? And let's just think about 6 minus 2i and -4 minus 3i, and maybe adding those two vectors together. So there's the way I just mentioned, which was 6 minus 2i plus -4 minus 3i, and adding those together. And I would get, say, 2 and a minus 5i. Or there's the way of thinking about these complex numbers as vectors, okay, instead of points. Later on, maybe much later, you'll come to see vectors and points as maybe not really that different. They share a lot of the same kind of properties, okay? Technically, they are different, but you'll see. Okay, so 6 minus 2i. And before, you may have just kind of plotted the complex number in the plane like that. I'm actually going to think of that as a vector. And I'm actually going to think of the negative 4 minus 3i as, instead of a point, thinking of that as a vector as well. Okay, so here's negative 4 minus 3i. What we're actually doing when we're adding those two vectors together is we're getting the sum of the two vectors, and that's some vector here. And the way I've put them together, you might remember from the other video that I could use this parallelogram method to add them. So if I make this parallelogram here, and I'll try to make, I'm going to cheat just slightly. So if I make this parallelogram, and my resultant vector is really this vector here, 2 minus 5i, over 2 down 5, is a result of adding those two vectors. So either algebraically or with the parallelogram method, I would get that result. What we actually want to talk about is another way entirely to write a complex number. So I could write it like 6 minus 2i. There's another form called polar form where it might seem more complicated, but it's actually more useful to think about complex numbers in polar form. And it gets kind of one of those another things in math where it's like, why are you making it more complicated sort of thing, where it's actually making it easier later on. But all we're going to do with it is just introduce it and practice writing complex numbers in polar form. But I got to talk to you about what polar form is. All right, so just imagine that I have this complex plane. And so here was my real axis. Here was the imaginary axis up here. And here was my vector, say x plus iy, right? And in my vector x plus yi, this length was x, this length was y. This is a right angle. We talked a little bit about r being kind of the length. You might kind of know what r is again. We used this formula a long time ago, but r was the square root of x squared plus y squared. We get that by the Pythagorean theorem. That's also referred to as the modulus of the complex number, which ties into what we looked at with the magnitude or modulus of vectors. So if I'm talking about like the magnitude or the modulus of a vector x plus iy, that's actually the square root of x squared plus y squared. So this is really just r, another way to think about it. And this is my picture right here that we're going to have. And this is my angle theta between the positive x and r. Okay. So the question is, instead of writing things in terms of x and y, so instead of locating a point in the plane by going over x and up y, the idea is, well, instead of getting the x and y, maybe I can tell you some angle to go. So go this angle and then go out this distance r to locate the point. So it's a different way of thinking about locating a point in the plane. Instead of going over x and going up y, I go some angle theta, and then I go some distance r from the origin, and I locate the point that way. And we refer to this as polar form. So equations from polar form, this is one of them right here. I've already written down. If I know x and y, I can find r. The other one is to find this angle theta. Useful equation is this tangent theta is, y over x, right? That is what the tangent theta is. And then I can use this to find our angle theta. Okay, the other thing is, when I have this complex number, I want to talk about writing x plus iy in trigonometric or polar form. So what do I mean by that? Well, x plus iy, what is that? Well, another way to think about x, well, I really want to get x in terms of r and theta because r and theta are going to be my new parameters to determine this point. So here, I know that the cosine of theta is my adjacent over my hypotenuse. That's x over r. So I know that x is r cosine of theta. To find y, right, I know that the sine of theta is y over r. Hopefully you agree with those. So y is r sine theta. So these are two other really important equations. And when I'm talking about my complex number x plus iy, I know that x is this r cosine theta. And I know this y is this r sine theta. So I really just plug those in. And you may see they both have a common factor of r, so I just factor that out. So it's r and then cosine theta plus I sine theta. Now, this is called the trigonometric form. Just to be really clear. And what we want to do is take a complex number, and I want to rewrite it in this form. Or we may take a number in this form and rewrite it in this form. Oh, by the way, I don't think I've used this, but a number in the form like x plus iy, like if I had like 2 plus 3i, that's called rectangular form. So the way that you've always written complex numbers is now going to be called rectangular form to kind of note the difference between the two. Okay, it's a lot kind of thrown at you right now, but I'm going to go through some examples. It's really not too bad, as you'll see. So, but I kind of wanted to explain a little bit where it comes from before I just throw a bunch of equations at you. All right. So hopefully you got all that down, and then I'm just going to do some examples to kind of shed some light into what we're doing here. All right. So let's do an easy one first. It's a little easier to go from polar form to rectangular because all I got to do is kind of evaluate this. So if I want to write this in a rectangular form, like I know what cosine of 45 degrees is, that's root 2 over 2. And I know what sine of 45 is, that's root 2 over 2. Right? And then I would just distribute this 2. So 2 times this, the 2's cancel. I would get root 2. 2 times this, the 2's here cancel, so I get, you can do I root 2 or root 2, I, either one. That's it. Maybe do another one where we're going to rectangular. That's pretty nice, isn't it? So maybe I have 8 times cosine of 270 degrees. And well, let me do this one in radians. Let's say I had cosine of 3 pi over 2 plus I times the sine of 3 pi over 2. And I wanted to know what that number was in rectangular form. So again, cosine of 3 pi over 2, think about the unit circle, that's just going to be 0. And the sine of 3 pi over 2 is going to be negative 1. So I really get this. And you may notice if I just multiply this by 8, I'm just going to end up with negative 8i. So there's no real part. It's what's called a pure imaginary number. Right? So just be on the y-axis and the imaginary axis on the complex plane. Okay, let's look at writing in trig form. Let's do write in trig form. Or polar form. Theta is in 0 to 2 pi. So theta is in radians is between 0 and 2 pi here. And our number is 1 plus I root 3. Okay. Let me write down what the polar form is, and then I think it probably becomes obvious what you need to do if you think about it that way. So I want it in the form r cosine theta plus I sine theta. That's our polar form. In order to write it in polar form, I need r and I need theta. R is really easy to find because all r is just going to be the square root of, say, 1 squared here plus root 3 squared. Right? So, and that is just 1 square root of 1 plus 3, that is just 2. So you're just using that formula where if I have x plus iy, then your modulus or your r is the square root of x squared plus y squared. Just using that formula right there. Okay? And then I also need to think about theta. So for that, maybe if you draw a picture, and we want this angle between 0 and 2 pi here, 1 root 3 So maybe I know that the tangent theta is, from this picture, root 3 over 1, or just root 3. When is the tangent of theta going to be root 3? Well, from the unit circle, hopefully you've seen this a lot of times, that angle in radians is going to be pi over 3. So if not, you can use calculator, but I think we talked about this quite a bit. Pi over 3. Tangent of pi over 3 is going to be root 3. And then I would just plug the r and the theta in. So this is really just 2, which is r. And theta was pi over 3, so cosine of pi over 3 plus I sine pi over 3. Good news is you can always check this. Like if I rewrite this in this form, I'm going to get that. And it's always kind of a nice check to do that. But that is what we want to do. Maybe look at one more like that. Let's look at, say, 43. Yeah, okay, pretty good on time here. So here our complex number is -5 minus 5i. So to get the trig form, again, I find our r, so I'm just doing square root of -5 squared plus -5 squared in this case. So that is in the year 25. That's the square root of 50, and that is 5 root 2. To find our angle theta, So -5, -5, that would be down here. So tangent of theta is going to be -5 over -5. Tangent of theta is going to be 1. Now, the best way to think about this is to think about what this angle is. So if you're down here and you're at a place where the tangent is going to be, a +1 again, what angle are you actually at? Well, you remember your pi over 4, your 3 pi over 4. This angle is 5 pi over 4, and that's the angle between 0 and 2 pi that we want, okay? So best way is just to think about it like this, because if I do the tangent inverse here, I'm going to get 45 degrees. That's really only telling me kind of this part here. And I want to think more about what is this angle from the positive x. And from my picture, I think it's pretty clear that that angle that we want is 5 pi over 4 here. Okay. So polar form then would be r is 5√2 times cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. Okay. And that will be it for this part. I think that's good enough. So did a quick review on 8.1, 8.2, very short assignment on that, and then we're also going to look at 8.3, and you're going to have a quiz on 8.2 and 8.3. So keep posted for the 8.